And today I'm going to talk about grounded neural generation. So I've chosen this title and topic to closely mirror the theme of the workshop, which is document grounded dialogue. So today we'll be talking about grounding, dialogue, and grounding in documents. So first, let me clarify what I mean by grounding. So there are two common ways we use the word grounding in our community. So symbol grounding refers to assigning meaning to words by external means, for example, relating language to vision. The other, maybe less common meaning these days, is grounding in dialogue, where two interlocutors coordinate their mutual understanding. And many recent really good papers adding to this discussion. So to complicate things even further, I'm going to talk about a third meaning of the term grounding in NLP. So for neural generation, we use the term grounding to indicate that we encode additional external knowledge. And this can take several different forms, which I will get back to later. And these additional encodings provide additional information for the decoder. So I wouldn't go as far as calling it constraints. This has another connotation, but I settled for the term restrictions in terms of providing richer input so that the model can learn to associate that richer input with the output. And anything which is ungrounded in the input I call a hallucination. So why do we need this additional grounding? Over the past years, researchers and machine learning practitioners found that actually vanilla end-to-end models don't work that well in practice. In particular, they found that these models produce outputs which are boring, inconsistent, and inappropriate. And in the following, I will review these challenges for 4 different sub-areas of grounded generation. In particular, I will be talking about data to text, where topics are tightly restricted by a data structure such as tabular data. Summarisation, where the generation is grounded in documents. Visual dialogue, grounded in pictures. And finally, open domain dialogue, which is usually only grounded in previous turns. So we go from the most specific restrictions to the least specific. And in total, I'm going to talk about 4 case studies, 2 of them on generation and 2 of them on dialogue. So the first case study is on data to text generation. And this part of my talk is based on a shared task called the End-to-End NLG Challenge, which I organized together with Andrei Dušek, who is now at Charles University, and Yekaterina Novikova, who is now at Winterlight Labs. So for data to text generation in the context of task-based dialogue systems, for example, we have an input which we, for dialogue system, call a dialogue act. More generally, we can refer to it as a meaning representation or data structure. And the task is to translate this data structure, meaning representation, into a sequence of text, the natural language target. So in the late 2000s, people have started to use statistical methods to solve this problem. And the first thing you had to do is to learn an alignment between the input and the output, which was a challenging task on its own. And you had to create annotations for this alignment. So in about 2015, researchers investigated neural methods to solve this problem, which alleviated the need to explicitly learn and model these alignments. So the below model shows the early T-gen model, which is LSTM-based sequence-to-sequence model with attention. So now you would obviously use something else like transformers, but the general idea still holds. So back in 2015-16, we were wondering how good these neural approaches really are and how well they would be able to model the complexities of natural language, since at the time they were mostly been trained on very simple formulaic data sets. So in 2017 we released a new data set, but this time we wanted to make sure that the target utterances were more varied and natural. So we used pictures to describe the task to our crowd workers, and we gathered about 50K of data points and released the data as part of our shared task. And we had 17 participants in this task, and there's also a high uptake of this data set outside the competition, one of the common neural energy data set these days. So I won't go into the details, but I just want to highlight one of our main results, which shows that neural systems, so the ones in purple in this table, produce output which is not consistent or grounded in the input. So the input is here on the first line. In particular, we found that neural systems hallucinate. So for example, this system introduces a price range which was not mentioned in the input. They tend to substitute values. So here coffee shop gets substituted for pub. And they also often forget to mention something, so the system omits to mention that it's a coffee shop. So this is obviously not great if you want to use a neural generation system as part of an end user application. So one question you might ask is, why does this happen? Why do these models hallucinate? So some people argue it's the model. In particular, there is something which we call exposure bias in neural natural language generation, which basically means that there is a discrepancy between training and test time. So as most of you will be aware, at train time, we use methods such as teacher forcing, where we use the ground truth as context. However, at test time, we use the generated noisy ones as context. And this is obviously especially problematic for autoregressive models. Another source for hallucinations might be the data. So in 2019, we released a clean data set for the E2E challenge, where we manually and semi-automatically cleaned some of the noise. And we were able to show quite substantial improvements in terms of semantic correctness, meaning less hallucinations and less omissions. And there's some recent work which suggests that one problem might be not having enough data. So for example, if you use pre-trained models, this seems to also reduce hallucinations and omissions. So what to do about it, other than using pre-trained models and massive amounts of data? You also might give the model more information, more knowledge. And we do that by reintroducing sentence planning. So the thing we try to get rid of to start with using neural models, we reintroduce it, however, still in an end-to-end fashion. So spoiler alert, this is a paper presented by my student Juno at the main ACL session. So only very briefly, so as I already said, so one of our main outcomes is that sentence planning helps correctness, so less hallucination, less omissions, and we still model it end to end. So this is different from the earlier approaches, which used a pipeline approach for sentence planning and surface generation, whereas we use HMMs to model ordering and aggregating information jointly. So these are the two steps of sentence planning. And then we use transformers for emission. We also use a semantic formalism called semantic role modeling to create alignments to increase the robustness to noise. And we show that we show this on the cleaned and the original version of the end-to-end NLG data. So another open question is how to reliably detect these hallucinations. So the good news is, for simple data to text task where you've got a closed domain, you can use scripts. So that's what we did in the E2E challenge. You write lots of regular expressions, or if you want to be more generic, you can use natural language inference, so between the input and the output. So that's something Andrei Dušek and his team proposed. However, what about tasks which have content selection? So where you can't be sure whether content was omitted on purpose or whether it was an error by the model. For example, summarization is one extreme case of content selection. And that's what I'm going to talk about next. So we are looking at abstract summarization using the XSum dataset. So you've got a source document, you've got the ground truth, which is generated by a human, and you've got the generated summary. And as you can see, the ground truth is very well grounded in the document. So you've got an Australian runner who unfortunately suffered life-threatening burns while she was trapped in a bushfire. However, she was still able to complete the Hawaii Ironman. When we look at our generated summary, however, we can see it's fluent. And it's also topic-wise somehow related. It's still about this Australian runner. However, part of it is a pure hallucination, at least when we compare it to the ground truth. And the standard method for doing that at the moment is using Rouge. So this is a reference-based metric. So there are two problems here. First of all, most of these data sets only have a single human reference, surprisingly. And this obviously has implications because there are many possible ways you can summarize a long document like the one in the example. Also, at the moment we are only comparing to this reference, and it might be that the fact which we consider an hallucination might in fact actually been mentioned in the document, just not in the ground truth. As I said, there's only one of them. So at last year's ACL we proposed a solution to this problem where we replace word-based and word-based measures such as Rouge or bird score with a fact-based measure that also takes the original document into account. So I just give you a brief overview of how this works. So we propose a new evaluation metric based on the idea of content weighting. So we are still using the human reference, but only to weigh which content is relevant in the source document. So these are the highlighted bits are the important parts according to the ground truth. And then we do the same thing again, but with the generated summary. And then we compare these two weights. And the more they overlap, the more factually grounded we consider the generated summary. So we show that this new metric correlates well with existing metrics such as Rouge or bird score, and also with human perception, where we get humans to highlight these the content. So you might ask how to get these highlights. So I already mentioned one way to do this is by manually highlighting the content. So this is totally reference free. Whereas we suggest an automatic metric, which is still based on the reference. However, it abstracts away from the actual surface form by using facts. So how do we get these facts? We represent them as a prop bank style frames, and we use semantic row labeling again. So semantic row labeling in a nutshell represents who did what to whom, where, and when. So all of these questions are obviously very relevant when you think about document summarization, especially news summarization. So we parse each sentence using an SRL parser and then generate a tree from a list of ordered facts. So ordered facts in our case are these SRL parsers. And once we got these SRL-based fact representations, we weigh these facts based on the ground truth in the generated summary and then measure the correlation between the content weighting produced by either. We also propose two levels of granularity, one based on the argument, so those are the leaves in the tree, and one based on the facts, that is the heads of the tree. So these two levels of granularity are similar to Rouge 1, Rouge 2, the idea. So I'm skipping right to some examples of our new metric, which we call corref-corre, so correlation of facts and correlations of arguments, to show you what sort of advantages this metric has. So compared to BERT score, corref-corre is better at identifying paraphrases. So the green text are paraphrases of each other, and the red text are hallucinations. So here you can see that our corref-corre is sensitive, is allowing these paraphrases, whereas BERT score is actually insensitive to whether it's a paraphrase or an hallucination for the same ground truth reference. Also, our corref-corre metric doesn't actually penalize content which is grounded or mentioned in the document, so that's the blue text here, but it is sensitive to, as I already said, to content level hallucination. So now I'm briefly going to talk about dialogue, and in particular dialogue which is grounded in images. So there are two commonly used data sets in this area. One is called VQA, which stands for Visual Question Answering. And in this task, the user basically asks a question, and the system answers this question by looking at the picture. So in this case, what is the moustache made of? Bananas. You wouldn't be able to answer this question without actually looking at the picture, right? It's not a very common type of moustache. The other data set is called Visual Dialogue, which extends this VQA data set, where the users can also ask follow-up questions. And these follow-up questions can contain dialogue phenomena such as reference or ellipsis. And in order to model these dialogue phenomena, you need to do both. You need to ground in vision, but also in the dialogue history, so in the previous dialogue turns. However, we found that VQA models, so models which perform really well for the VQA task, also perform extremely well for the visual dialogue task without modeling history. And we're obviously wondering, why is that? So again, this is a paper presented at last year's ACL. So again, I won't go into the details. I will skip right to our results. The one thing I want to briefly mention or explain is about the task. So the visual dialogue is a discriminative task. That is, you don't ask the model to generate a response, but to select one. And there are two subtasks. One is about ground truth selection, and one is about ranking, where you get a set of possible answers, including the ground truth plus some distractors. And we have modeled this task using the top performing VQA model. So this is without history, and that's our baseline. And then we added three possible ways to encode history, two of them with early fusion and one of them with late fusion. And what our results show is that, first of all, encoding or grounding in history actually doesn't seem to help much. So you can see that compared to the baseline, they improve a little bit, but not very much. The other result is that for the ranking task, we can observe that the results are actually very inconsistent with respect to the two metrics we're interested in. In particular, we see a very sharp drop in NDCG. So let me briefly explain about this metric first. So NDCG assigns a value to all candidates which are considered as somehow relevant or semantically related to the ground truth answer, which in theory is a good idea, but in practice means that the model settles for very generic non-committal answers, because these will always somehow be relevant, right? So for example, we see that a lot of the answers are non-committal or generic answers, such as not that I can see, I think so, I can't tell, not sure, yes it is, not really, maybe. So again, we have neural models which generate boring answers which are not grounded. So now to the first question. Why do history encodings not help much? And in order to answer this question, we conducted a crowdsourcing study to find out how much people require history to understand what's going on. So we got crowd workers to do this task and indicate whenever they needed to know the context, which we didn't show them. And it turned out that only in 11% of the questions, crowd workers felt they needed more information from the context to confidently answer the question. So for this confirmed subset, for these 11%, we re-ran our model, so we re-evaluated our models, and we now can actually see that encoding history actually does help. So we get an uplift of about 7 points in MRR and 4 points in NDCG using these history encodings. So that's good news. However, the bad news is that most of the visual dialogue dataset is actually simply multiple rounds of VQA rather than dialogue. So my final case study is on open domain dialogue, and I won't be able to go into any details because of time constraints. I will briefly advertise two papers here. One is by my student Karin Sevignani, published at this year's ACL, and one is by my collaborator Emily Dynan at Facebook AI Research. And this paper will hopefully appear on arXiv very, very soon, so stay tuned. So grounding for open domain dialogue. You might say, but open domain dialogue is just chit chat. How can that be grounded? So one answer is, in order to generate a coherent reply, you still need to ground in a previously mentioned topic, i.e. you need dialogue history again. Anything which is unrelated, I call a hallucination here, and anything which is generic or boring is an omission. And in an EMLP paper a couple of years ago now, we present a simple approximation of lexical coherence using embedding distances. So that's one way to measure this. The other question you might ask is grounding in dialogue history or context actually enough? What about that stochastic parrot argument by Bender et al.? At this point, I assume you are all aware of this paper. So in that paper with Emily Dynan, which I mentioned, we argue that stochastic parrots for a dialogue system includes a set of specific problems which we subsume under safety. So first of all, large language models as well as end-to-end conversational AI systems are known to generate inappropriate output. Think, for example, of Microsoft's chatbot Tay, where the first example is taken from. But also our own system, an early version of our own system, which we entered in the Amazon Alexa challenge, said some pretty inappropriate stuff. Obviously, what you consider appropriate depends on the context, the user, the culture, and so on. The second problem we identify is that neural systems often agree with whatever the user says, even when it's something hateful or biased, as in this example. The final problem is when the user seeks counsel or advice from the system, for example about mental health or financial advice, the system can actually cause some severe long-term harm. So you might ask again, where does this come from? Some might argue it's the data. So in the stochastic parrots paper, a stochastic parrots paper suggests that training on large data sets from the internet might be the problem. Another line of argument again is that the model, so these large neural models only learn form but not meaning. So basically they don't know what they're talking about. And this is an argument brought forward as the octopus test in Bender and Koller at ACL last year. One might also think that we don't have the right type of evaluation procedures. For example, BERT score measures the similarity with the data, and in some cases we actually do not want to mimic the data. And finally, it might also have something to do with the design, as these systems tend to be modeled as human-like with female voices, which might provoke additional safety critical issues such as the user abusing the system. And these papers are two papers by my group which investigates that issue. So again, what to do about it? One way might be to stop being a parrot and actually take initiative. And in the ACL paper with my student Karen, we propose a mechanism based on knowledge graphs to introduce and transition into new topics. So obviously we also use some neural generation for that, and we also release a new corpus. So check out Karen's paper. So to summarize, I have talked about grounded response generation, where encoding additional input helps to restrict the output. I have presented 4 case studies with different degrees of specificity, from tightly constrained data to text to loosely constrained open dialogue, with document summarization, visual dialogue somewhere in the middle. And for each of these case studies, I have discussed challenges related to ungrounded generation, which often is boring, inconsistent, and inappropriate. And finally, I have presented model improvements and new evaluation metrics to alleviate these issues. So thank you so much for listening, and I'm looking forward to get your questions.